Hello, this is Kuntal Chakraborty, Assistant Professor of Electrical Engineering Department, Greater Kolkata College of Engineering and Management, JIS Group. I'm just going to give a lecture on an important topic, that is instruction sets of 8085 microprocessor. I'm just going to explain the logical instructions. Basically, logical instructions, first instruction is for the logical AND operations, that is ANA-R, ANA-M. It means the AND operation be the content of the register with the content of the accumulator, and ANA-M is the content of the memory that is specified by the HL register with the content of accumulator, and both cases the results that will be stored into the accumulator, and sign 0 parity are modified in the flag register, and the carry is reset and auxiliary carry is set. So example like ANA-C, ANA-M means the content of C that will be ANDed with the content of accumulator, and result that will be stored into the accumulator. ANA-M means the content of the memory that is specified by the HL register with the content of A that will be ANDed, and the result that will be stored into the accumulator. Both the cases sign 0 and parity are modified, and carry is reset as well as auxiliary carry is set. So that is the AND operation with the register and the memory. And AND operation with the immediate data, at this time we are using the ANI instructions, where we will actually provide a 8-bit data directly. So in this case sign 0 parity are modified, and here the carry is reset and auxiliary carry is set. So now example is ANI 83H, the 8-bit data 83H that will be ANDed with the content of the accumulator, and that will be stored into the accumulator, the result that will be stored into the accumulator, and there will be some effects on the flags that I already discussed. Next is the OR operations, OR with the content of register and OR with the content of memory. Here similarly the register, it may be any general purpose register B, C, D, E, H, L, and in case of memory, basically this memory is specified by the HL register pair, and the content of this memory that will be ANDed with the content of or with the content of A, and the result that will be stored into A. Here similarly sign 0 P are modified, and carry and auxiliary carry are reset. Example like ORA D, ORA M. In case of ORA D, the content of D that will be OR with the content of the accumulator, and the result that will be stored into A. ORA-M, that is OR operations of the content of the memory that is specified with the HL registers by the HL register with the content of A, and the result that will be stored into the accumulator. And here the sign 0 parity are modified after the operations, as well as carry and auxiliary carry that will be reset. So this is the OR operations. And next is a ORI, that is the OR operation with the immediate 8-bit data. So this is same as ANI, means the immediate data that we have to provide for the operations or operations. So that 8-bit data that will be ANDed OR with the content of the accumulator, and the result that will be stored into the accumulator. And here similarly sign 0 parity flags are modified, and carry and auxiliary carry are reset. Example like ORI 55H, the 55H 8-bit data that will be OR with the content of the accumulator, and the result that will be stored into the accumulator, and we will get some effect on the flag that is on sign 0 and parity flag, and carry and auxiliary carry that will be reset. Next is the XRA operation, that is the XOR operations. XRA with the R and M, that is similar like AND and OR operations, that is the content of the register and content of the memory. XOR the operation is done with the content of the accumulator, and the result obviously stored into the accumulator, and here the sign 0 parity are modified as well as carry and auxiliary carry are reset here. Example like XRA E and XRA M, here means the content of E, the XOR operations with the content of E with the content of accumulator, and the result that will be stored into the accumulator. XRA M is the content of the memory specified by the HL register pair with the content of accumulator, and the result that will be stored into the accumulator, and obviously we will get some the effect on the flags. So this is the XOR operations. Next is the XRI, that is similar like ANI and ORI, that is immediate 8-bit of data that we have to provide for these operations. So example like XARI 82H. So the content of accumulator and 82H, the XOR operation that will be done with the 82H and content of the accumulator, and the result that will be stored into the accumulator, and we will get the effect on the flags. So that is the XOR operations. Next is a compare operations, that is CMP. By using, we can compare the content of the register as well as the content of the memory that is specified by the HL register pair. So here what is happening in case of a comparison, if the content of the accumulator is less than register or the content of the memory, content of the register or content of the memory, then the carry flag that will be set. Similarly, if the accumulator, the content of the accumulator is equal the content of the register or the memory, then the 0 flag that will be set. And if the content of the accumulator is greater than the content of the register or the memory, then the carry or 0 flag are reset. So this is the conditions where we can get whether the accumulator is greater than or less than or equal to with the content of the register or memory. So here the example like compare CMP-E or CMP-M means the content of E that will be compared with the content of accumulator, and the flags reflected, the results of the flags, that is after the results, the flags that will be reflected as I already discussed. Similarly, the CMP-M, the content of the accumulator with the content of the memory that is compared, and the effect of the results that we already discussed. If it is less than A, then the carry flag is set. If it is equal to content of the accumulator, that is same with the content of the register or the memory, then the 0 flag is set. And if the content of the A that is greater than the register or the memory, then the carry and 0 flag that are reset. Next is a CPI, that is we will compare with the immediate 8-bit of data. So here the operations is same, but here only we are actually providing a 8-bit of data that will be compared with the content of the accumulator. And here similarly, if A less than data, then the carry flag that will be set. If the content of the A that will be equal to the data, then the 0 flag is set. If the content of the A that is greater than the data, then the carry and 0 flags are reset. So this is the CPI operations. Next is the RLC. Here the basically rotate accumulator left, the 1 bit that will be shift into the left side. So basically the bit D7 is placed in the position of D0 as well as in the carry flag. So that is the operations by which 1 bit that will be shifted into the left side, and Z, parity and auxiliary carry are not affected here. Also the sign are not affected here. So what is happening here, the content of the D7 the bit that will be shifted into the position of D0 as well as into the carry. So the change of carry that may occur. So example like RLC. Now next is the RRC. It is basically the bit D0 is placed in the position of D7. So this is basically rotate accumulator right, means the content of the accumulator that will be shift by a 1 bit, means the content of the 0 that will be placed into the D7. So here as well as into the carry flag also. So the carry flag may be changed, but here the sign 0, parity, auxiliary carry are not affected here. So that is the RRC instructions. Next is a RAL, that is a rotate accumulator left through carry, means the D7 bit that will be placed into the carry flag, and the content of the carry flag that will be placed into the D0 bit. So here the content of the D7 bit that will be placed into the carry flag as well as the content of the carry that will be placed into the D0 flag. And here the carry is modified, but sign 0, parity, auxiliary carry are not affected. So that is the operations of RAL, that 1 bit that can be shifted through the carry into the left side. Next is the RAR, that is the rotate accumulator right through carry. So the content of the accumulator that can be shifted by one bit through the carry, means the bit D0 is placed in the carry flag, and the carry flag is placed in the most significant position, that is the D7. Similarly, here the carry is modified, but sign, zero, parity, auxiliary carry are not affected. So that is the RAR instructions by which the one bit that can be shifted into the right side of the accumulator through carry. Next is a CMA, that is the complement instructions. So the content of the accumulator that will be complements by 1, that is one complement done if you use this CMA. The accumulator, the content of the accumulator that will be complemented by 1. So that is the ones complements operations basically. So example like CMA. Next is a CMC, that is a complement carry, means the carry flag that will be complemented, means flag are affected, carry flag that is affected. So the example like CMC, if you use it, then the carry flag that will be complemented. If it is 0, then that will be 1. If it is 1, that will be 0. So next STC, that is a set carry. If you want to set the carry, if you want to write the carry as 1, then we have to use STC. So example like STC. Next is the branch instructions. Branch instructions, it may be, we have two types of jump instructions. One is a conditional jump and another one is a unconditional jump. In case of unconditional jump, we have to use this instructions JMP with a 16-bit address where it the program sequence may transferred. So this jump 16-bit address means the jump unconditionally into a particular address. So here example like JMP2E3FH. So if we write these instructions there, then the program sequence that will be jumped to into this particular address. So that is the unconditional jump. We don't have any conditions by which the jump can be made. Next is the conditional jump, and in this case where the program sequence that can be transferred to a particular locations by using some conditions. So we need some conditions to transfer the program sequence to a particular condition. So here first example is like JC. In case of if the carry flag is set as 1, so at that time that jump that can be made to a particular location. So if the carry flag is reset as 0, reset means if the carry flag is 0, at that time we can use JNC instructions and the program sequence that can be transferred to a particular locations. And JP, if the result is positive, at that time the jump that can be occurred. JM, if the result is negative, if the sign flag is set as 1, at that time jump that can be occurred. JZ, where the 0 flag is set, when the 0 flag is set means the result is 0, at that time the jump that can be occurred. JNZ, if the 0 flag is reset, at that time jump that can be occurred. JPE, jump on parity even, if the parity flag is set as 1, if we have the even parity, so at that time jump can be occurred. JPO, if the parity is odd, the results parity is odd, at that time jump can be occurred. So these are the conditions by which the program sequence that can be transferred to a particular location. So these are the conditional jump. And in case of jump instructions, we don't have any conditions, so we don't have any conditions to jump to a particular location. So jump instruction is unconditional instructions. Next is a conditional subroutine call. But in case of call instructions, we can basically call a particular subroutine. So by using a CALL instructions, so we can call a particular subroutine where we don't need any conditions. Subroutine is nothing but a program that is written into a particular locations. So basically every time we will call these instructions, so we can use a conditional call as well as unconditional call. So in case of unconditional call, we can use a CALL instructions, and we have to provide a particular address where the subroutine is written. And in case of conditional call, we have to use these instructions like CC. In case of CC, when the carry flag is set, then only it can call the subroutine. CNC, when the carry flag is reset, then only it can call the subroutine. If the parity, if the result is positive, then we use the CP for the conditional subroutine call. And in case of the sign flag is set as 1, means the result is negative, then only we can call the subroutine. In case of the result is 0, then we can use the CZ for the call of subroutine. If the result is non-zero, then only we can call the subroutine. CP, if the parity is even, at that time we can call the subroutine. CPO, if the parity is odd, then only it can call the subroutine. So these are the conditional subroutine call instructions by which we can call the subroutine. Next is the return instructions. This is basically used to return from the subroutine, and when the return instruction is introduced, at that time the two content of the stack of the top two content of the stack, that will be popped from the top of the stack, and that will be stored into the program counter, and the content of the program counter that will be placed into the address bus to return into its previous position. So that is the return instructions, and we don't have any conditions to return from subroutine. And to return from subroutine conditionally, we need this kind of instructions. So we can use RC. If their carry is set as 1, then only the return that can be made from the subroutine. And in case of RNC, when the carry is reset, at that time the return that can be made only. If the parity, if the result is positive, then RP instruction used to return from the subroutine. RM, if the result is negative, then only the return that can be made. RZ, if the result is 0, then only the return can be made by using RZ instruction. RNZ, if the result is non-zero, then only the return can be made from RNZ. RPE, when the parity is set as 1, means the even parity is generated in the result, then only the return can be made from the subroutine. So these are the conditions by which the return that can be made from the subroutine that is called by the microprocessor. So next is the RST instructions that is basically introduced for the interrupt operations. So this is basically a word byte of instructions. So we have 8 RSTs. One of these RSTs is introduced whenever the interrupt occurred through INTR. So this is used the conjunction with the interrupts and inserted using the external hardware. So whenever any of these instruction is introduced, it has a particular locations, the program sequence that will be transferred to these particular locations. So however, this can be used as software instructions in a program to transfer the program executions to one of the 8 locations also. So these addresses are already specified in this diagram. Next is a machine control instruction. First machine control instructions is NOP, that is the no operations. So basically, if you introduce NOP, then no operation is performed. The instruction is fetched and decoded, but however no operations is executed. So this is the NOP instructions, and this is machine control instructions. And next is the halt instructions, and this is basically if you use halt instructions, so enter is basically into a wait state. The machine basically enter into a wait state. So the CPU finishes the executing the current instructions and halts any further executions, and an interrupt or reset is necessary to exit from this halt state. So that is also a machine control instruction. Next is machine control instruction is DI. If you want to disable all the interrupts except trap, then we can use the DI instructions to disable all the interrupts. Next, EI instructions. If you want to enable all the interrupts, then we have to use, except the trap instructions, then we have to use the enable interrupt instructions, that is EI. This is also a machine control instruction. Next is the RIM instructions, that is the read interrupt mask, by which we can read the interrupt, the pending interrupts of RST 7.5, RST 6.5 and 5.5, and this is basically a multi-purpose instruction that is also used to for the serial data output instructions. Next is a RIM instruction, SIM instruction, that is set interrupt marks, by which we can set the interrupts as we can set the mask of these interrupts of 7.5, RST 7.5, 6.5 as well as 5.5. So we have a particular set of data that is actually we can write into the accumulator to set a particular interrupt of RST 7.5, 6.5 as well as 5.5. So that can be used to set as well as reset of mask. And that is the instruction is used here, the SIM. This is also a machine control instructions. Now we are going to discuss the addressing modes of 8085 microprocessor. In case of 8085 microprocessor, we have 5 addressing modes. One is the immediate addressing modes, next is the register addressing modes, direct addressing modes, indirect addressing modes, implied addressing modes. First, I am just going to explain the immediate addressing modes. In case of immediate addressing modes, in this mode, the 8 or 16-bit data is specified in a instruction itself as one of its operands. So the example like MBI E2FH, so T2F immediate data that will be stored into a particular register, that is E. LXI B3090H, here the 16-bit data that will be stored into the BC pair. So ANI 30H, that the 30H that will be ANDed with the content of the accumulator. So here the immediate data is specified into the operand. So that's why this kind of instruction is called the immediate addressing modes. So now next is the register addressing modes. Here in case of register addressing modes, in this mode the data is copied from one register to another. So example like MOV D, E, the content of E that will be stored into the register D. MOV B, D, the content of D that will be stored into the content of into a B register. So here in this case the data is copied from one register to another. That's why this kind of register addressing modes is called the register addressing modes. Next is a direct addressing modes. In this mode the data is directly copied from the given address to the register. Example like LDA 2008 means the content of the 2008 that will be stored into the accumulator. So here the direct operation is going on, means the content of 2008 address that will be stored directly into the accumulator. So in this mode the data is directly copied from the given address or register to the register. So that's why this kind of instruction is called the direct addressing modes. Next is the indirect addressing modes. In this mode the data is transferred from the register to another by using the address pointed by the register. Here the example is MOV B, M. Here the content of the memory that is specified by the register pair, that is a HL register pair, and that will be stored into a B. So here the indirect operation is going on. So here the content of the memory means that is specified by the HL register pair, and that will be stored into the B. So indirect addressing modes is happening here. Next is a implied addressing modes. So this mode doesn't require any operand. So the data is specified by the opcode itself, that is CMPC, that is compared with the content of the accumulator with the content of the C. So this is the implied addressing modes. So these are the addressing modes of 8085 microprocessor. In case of 8085 microprocessor, these 5 addressing modes we have. So we already discussed all the instruction sets as well as the addressing modes of 8085 microprocessor. Thank you.